Hello everyone. In the previous video, we had addressed an example problem on the circular plate which was subjected to uniform loading and it was clamped all around the periphery. In this video, we are going to consider a slight variation on that problem in the sense that instead of a uniform loading on the circular plate, we are going to consider a concentrated load acting at the center. So how do we solve this problem? So first of all, let us write down the governing equation. I will not again repeat the initial discussions, or rather lengthy discussions that I had in the previous video while starting out this problem. Rather, I'll start from an intermediate step, which was to consider the governing equation. So we had the governing equation in this particular form. Now please note that this Q was like a distributed load, but here we have the concentrated load. So here directly we have a challenge how to match this thing in this form. So what we do here is so suppose let us treat it in an engineering sense. Suppose we do write it like F. What is the harm here? Well, you see, if we write like this, first of all, there is the problem that this entire governing differential equation has to be valid in the domain 0 to R. Well, if that is so, then it would appear to us that nowhere or wherever we are sitting along this radius, this F would be acting. That is what would be represented by this, or that would be the meaning of this governing equation if we had to simply write it like this. But that is certainly not true, because this F is only acting at R equal to 0. How do we represent that? There is another issue here, that this F has the unit of Newton. If you go back to the previous video, you should note that Q that had the unit of Newton per meter square. Just like the left hand side of this equation, this has the unit of Newton per meter square. So there again is a discrepancy. On the left hand side, we again have the same kind of terms, so that unit remains unchanged as Newton per meter square on the left hand side, but on the right hand side, as written, this is Newton. So how do we overcome these two discrepancies? First of all, regarding the applicability of this F, and second regarding the units. So this can be solved by considering the Dirac delta. So if we write like this, the Dirac delta of R, with the understanding that we are actually writing it like R minus 0, what we actually imply here is that this entire term will be applicable only when R is equal to 0. Okay, anywhere else that you are sitting on R, okay, R by 2, capital R, R by 3, anywhere other than 0, this term is going to be 0. Regarding the unit, if we are saying that this is indeed the correct expression, then it must mean that this Dirac delta has the unit of 1 by meter square, and that is actually correct, because I mean it seems a little weird to think of this Dirac delta having some unit, but you see, usually we think of the Dirac delta or the definition in this fashion from our undergraduate days, that we have this thing. So the Dirac delta is defined in this fashion, that the integration from minus infinity to infinity, that is equal to 1. What will be the counterpart of this in the radial or the polar coordinate system? So what we say here is that we have this, but then we have to actually carry out the integration in this polar coordinate system properly, and the counterpart of what we have written above would be by considering this kind of an elemental ring of radius small r and thickness dr, and this integration will be from 0 to infinity, and this thing will be equal to r. Now you note immediately that if you are considering the r to be some sort of a simple number as part of the real number line, then it certainly does not have any unit. But suppose it were to represent actual dimensions, then this particular part, this would have the dimension of meter square, and then naturally, because this right hand side is dimensionless, this would be having the unit of 1 by meter square. And that is why when we come here, this part has the unit of Newton, the F has the unit of Newton, the Dirac delta of R, that has the unit of 1 by meter square. So overall this is Newton per meter square, matching with whatever is there on the left hand side. Okay, all that is fine, but how do we solve this? Okay, so the trick is to really exploit the condition that this right hand term is indeed 0 at r equal to 0. So what we are going to do is, instead of considering this governing equation, which is valid over the domain 0 to r, 0 included, we are going to consider a slightly different form of the same problem, like this, where we say that r lies in the interval 0 to r, but the left hand side is open. Okay, so how does that help us? Well, you see, the moment you have this kind of an equation, it is very easy to, well, it is quite straightforward. I wouldn't say very easy, but quite straightforward to do the integrations repeatedly in exactly the same fashion that that I have asked you to do in the previous video, where on the right hand side you had an extra complication in the form of that 64 beta that is not even present. So what you will end up here is, you can immediately write down this the form of this thing as a r square ln r plus b ln r plus c r square plus d. Okay, now the question comes about like what should be the boundary conditions. Well, we can immediately write down whatever is happening at r equal to small r equal to capital R. No problem there. It is exactly the same conditions as before, which is w is equal to 0 and dw dr is equal to 0. So the deflection is 0 and the slope is 0 at the all around the periphery, because that periphery is clamped. But again, we have to deal with the condition or the question that what do we do? What do we do regarding the other two conditions which are missing? Well, just like in the previous problem where we had the uniform loading, we can still argue for the fact that W should again be finite. Okay, we have this form for the W. We can see here that there is this rather inconvenient looking term here, and we would very much like it to be finite, even though we have kind of avoided actually going to r equal to 0, but we still have to go to r very close to 0, and even then this term is problematic. So what we say here is that as r tends to 0, W should still be finite. And if that is so, we can immediately conclude that B must be equal to 0. So we are left with this term, and this term. Okay, so we have two conditions which are yet to utilize, but we need another condition, and this is where the real challenge of this problem comes about. Okay, so what is that extra condition? You please note that in this entire story, we have completely avoided dealing with this applied force F. Now that is the prime mover of this problem, the prime driver of the entire deformation. We cannot avoid dealing with it. We have to take this into account. So how do we take this into account? So so please do not think that just like before we can get away with imposing the condition that the moment should be finite. We have to somehow incorporate the condition that that this F is influencing the deformation. So how do we take that into account? Well, you see, there is a little hint here. The hint is in the nature of this applied load itself. It is the force F. So what is directly connected with this force F? Well, uh, you can start thinking about the shear force. So if you think of the shear force, it's something like this. Okay. So what we say is, uh, suppose you consider a uh, a part of this okay, a smaller ring uh, which is concentric with this circle, and let this be of some arbitrary radius r. Please note that if you really zoom into it, maybe this portion, if you zoom into it, you will find that that is actually having a certain thickness, which we have integrated throughout uh, because of the way that we have derived our governing differential equations. But that has physically a certain thickness, and over that a shear force per unit length Q is acting. Okay, so that is the QR. So what exactly is going on here? How can we write this thing properly in terms of the things that we have written down in our derivations? Okay, so so let me go to the next page here. Uh, what I want to write here is that Q times twice pi r, that should be equal to F. So this Q, it is acting all around this periphery which has the radius of r, so that length is twice pi r, and no matter what radius of this periphery I take, this should be actually true. The condition that I have just written down here, Q times twice pi r, that should be equal to F. Okay, so uh, all that is fine. I mean, physical understanding is fine, but what about the expression itself? Okay, and please note that this is the QR. So this QR, it is actually corresponding to the Qn, which we had written down during our derivations, and that, please remember, was nx qx plus ny qy. And this thing, this qx itself, that is del mx del x plus del mxy del y, whereas this qy, that had the form del mxy del x plus del my del y. Now, if we were to carry out all the substitutions, that would be of course a little bit lengthy. So I encourage you to perhaps do this bit using symbolic Python in Jupyter Notebook. And in fact, this is another problem that I have given in the problem sheet. So I won't go into the lengthy derivations of this. It is just I mean, you have to do it patiently, or you have to do it cleverly in symbolic Python or any other computer algebra system. But eventually the expression that you will obtain will be ddr of del square w, and which is ddr, and this del square w, this is just the Laplacian. So we have this thing. Okay, now what we have to really do is to utilize this expression back here and equate it to f. Well, let's try this. We already have from our previous page this expression for w. All that you have to do is to obtain the expression somewhat patiently here. So what I'll do is I'll go to the next page and carry out the steps. So the first thing, of course, is that we have to do this dWdr. That gives me twice AR. I don't need to consider this P, that is 0, and I don't need this D also. I think I made a mistake here. I need another term here because this actually involves the r square ln r. So I need to write this as ER also, because this ln r would be contributing a 1 by r. Next, for so I should not be blindly doing this d square w dr square, because you note that in the previous page I had this r dw dr. That's what I need. I'll do that. Twice ar square ln r plus ar square plus twice CR square. Next, I need to do a DDR of this. So that gives me a 4AR ln r plus twice AR plus another twice AR from this term plus 4CR. And let me just check. So I have completed up to this DDR. I need to do a 1 by R. If I do a 1 by R here directly, so that goes, that goes, that goes, and that goes. And finally, if I have to carry out this last DDR, I'll end up with well, this doesn't contribute, this doesn't contribute, and this doesn't contribute, because these are just constants. This is just 4a plus 4c, so I don't need to worry about it. And let us not forget that this capital D is also present, so I have this term. So this entire thing is the QR, and the condition that I need to impose here is QR twice by R, that is equal to F. So this gives me 4AD by R twice by R, that should be equal to F. And this is very good that this R and R cancels, and that gives me the expression for this unknown constant A as F by 8 pi A. Oh, sorry, 8 pi D. All right. So currently, I know about my B, that is 0. I know about my A. All that I don't know is C and D. But for that, I have my my boundary conditions at R equal to capital R. So I can quickly go to that. So this A is already known to me, as I've just found out. So I need to just use that R equal to R, W is equal to 0. So that should give me A R square ln R plus C R square plus D is equal to 0. Furthermore, at R equal to R, I have dW dr equal to 0, which means I can just go to the previous page and copy out this expression for dWdr. But I have to be careful that this small r is actually capital R here. Because we are sitting at the periphery now. Okay, so these are basically two linear simultaneous equations involving the unknowns C and D. Please note that A is already known to us, and this second equation that we have just obtained, that is simply this involving this unknown C. A is already known here. So what we can simply do here is to write this as minus A R ln R minus half A. Since A is known to us, C is immediately known to us, and finally we go back here, this D can be written as so. In the interest of saving time, I'll not just substitute this expressions of C and A here, but the fact remains that whatever we needed to find out, we have found out here. So basically this W is known to us now. Okay, so you see the two big challenges involved in this problem was to take care of the governing equation properly, and also this special condition involving the shear force. So on that note, I will end this video. Thank you very much.